Okay, let's take a look at some more circle rules. So let's take a circle and draw a radius going straight down and drawing what's called a tangent. I'm going to do that again. It has to hit it perfect. I'm going to do it again. Try a ruler. I'm using a digital screen. It has to hit it perfectly and it has to be perfectly flat. Tangent. And you can see in the diagram, I've labeled the diagram and put all of the names of all the things on the diagram. And the rule is the radius is perpendicular to a tangent. So no matter where it is on the circle, if you draw a radius to it, it's perpendicular. You may use this rule, you may have to find out this rule from other information, etc. But anytime we can use this rule, we have to. So let's go for another circle and let's draw a center of the circle and a radius, and this time a chord. So we also know that the radius is perpendicular to the chord, so we get 90 degrees there and there. A very similar rule, because if you can imagine this being the tangent, and if we know it meets at 90 degrees, and I just move this to the left of a bit, well, it's exactly the same rule as we just did off to the left. So radius are perpendicular, meeting at 90 degrees, to tangents and chords. Okay, let's take a circle and let's cut it in half. If I draw a triangle meeting the outside, the inscribed angle on the outside of the triangle is 90 degrees. Okay, let's take a look at another rule. So we've got a circle and a point over here, and a tangent here, and a tangent there. You know what? There's a tiny little red line in the middle circle above. I'm just going to draw it in red right now. It's called draw in a radius. It's always very helpful to draw in a radius. So for example, if this diagram didn't have radiuses, I would put them in. And I know that tangents are perpendicular to radiuses, sure. I'm also going to draw a radius through the circle to the exterior point. And what we have here, we have right angle triangles. And we know that the tangent from the point of tangent to the circle is equal to the other tangent to the exterior point. So this length right here is equal to this length right here. Very useful, because then we can apply Pythagoras' theorem. Okay. Another rule off to the right there, we have a circle, we have the center, we have two chords. And if I know that, for example, these chords have equal length, we also know that they meet at right angles. If those radiuses to the chord are equal length, we know that these two are equal and these two are equal. And for that matter, I did not finish the rule above. I'm going to erase the radius that we put in. Now, we know that if the radius is perpendicular, it cuts this line in half and both those sections are equal. And we can apply that exactly and expand it to this further rule. So again, big red, middle, top, forgot that it also cuts it in half. So not only is it perpendicular and meets at 90 degrees, it also cuts it in half. Okay, another rule. So let's take a quadrilateral. I'm sorry, I'm going to do that again. Let's take a quadrilateral just like the notes. And let's call it angle 1. You couldn't say angle in front of it. You don't have to. Let's do it. Fine. Angle 1, angle 2, angle 3, angle 4. And as you can see in the notes, angle 1 plus angle 2 add to 180. And it turns out angle 3 and angle 4 also add to 180. We call that rule opposite angles in a cyclic quadrilateral are equal. So if we have a quadrilateral that hits all 4 sides of the circle, then we know that the opposite angles add to 180, and therefore all of them add to 360. That's all in the notes. Continuing, we have another circle. Let's put a tangent on there, and let's put an angle, a triangle in the circle. What we know is this angle right here is equal to this angle right here. So whatever they are, in the notes they're 60. We call that rule an angle between, I'm going to do it in big red, an angle, you know what, medium red. So I'm going to do the angle between a chord and a tangent is equal to the angle inscribed opposite of the chord that we just outlined. Okay, so this next rule about polynomial, about multiple-sided shapes, is a little bit of a foundations thing, but sometimes they see it in geometry, so let's just go through it. So let's take a pentagon, which means that all the angles, all the sides, are equal. And if it's regular and all the sides are equal, you know that all the angles are equal. And we can figure out what the angles are by redrawing the shape and cutting the shape into triangles not overlapping. We have 1, 2, 3 triangles. Therefore, we do 3 times 180 is equal to 540. Then we divide it by the number of sides. A pentagon has 5 sides, and that's equal to 108, which means that each of these angles are all 108. As you can see in the notes, I put 108 in all the locations. And those are called interior angles. And then we have a line that comes over here, and on the outside here we call this, excuse me, don't tick that line, excuse me. We call this an exterior angle. And if I redraw that system directly above and I know this is 108, well then this is 72. Angles on a line add to 180. And you can see all of the different formulas, how to find different things, but I just like sometimes not going that far into formulas and just sticking to it. So let's review the rules. Rectangle, circle, squares in big blue. Top left. The radius meets the tangent at 90 degrees. Middle top, big blue. The radius meets the chord at 90 degrees and cuts it in half. And it's a very good idea to draw in another radius to make a right angle triangle. Top right. If we have a semicircle, the inscribed angle is 90 degrees. Middle left. If we have what's called an exterior point and the tangents meet it, well, then the tangent lengths are equal and we can tick those tangent lengths. Very helpful to draw in these radiuses, and we know that they meet the tangents at 90 degrees, and we have right angle triangles, and we can use Pythag. Okay, middle right is a further definition coming from middle top. If you have 2 radiuses to 2 different chords, and we know the length to the chord, it's not actually a radius, but a segment from the center to the chord, if those are equal, we know that both of the sections are all equal. each of those chords is divided by 2, and both sides are equal in red. Okay, middle left below, opposite angles in a cyclic quadrilateral add to 180, and they all four add to 360. Middle right below, the inscribed angle is equal to the angle the inscribed angle opposite of the chord is equal to the angle between that chord and that tangent. Notice there's a tiny little gap in the notes from the tangent to the circle. Obviously, I've kind of overlapped it here. And then if we want to find interior or exterior angles of any size shape, at the bottom, we divide the shape into triangles. We multiply that number by 180 because there's 180 degrees in a triangle. We divide that number by the number of sides, and that gives us the interior angle. And we can find the exterior angle by doing angles on a line add to 180. So again, we have to be able to see multiple complex problems and be able to apply any of these laws in any order wherever we can or we want to. We just can't break any of the laws.